So far, we've seen how to analyze fMRI data using different software packages, such as AFNI, SPM, and FSL. Now that you know the relative strengths of each one, what if we could combine all of their strengths into a single pre-processing pipeline? Sort of like creating a superhero, like Captain Planet or Pootie Tang. We can do this with fMRIprep, a software package that uses standardized pre-processing on BIDS-compliant fMRI data. This pipeline uses tools from different fMRI software packages, such as AFNI, FSL, ANTS, FreeSurfer, and NiPipe, to perform specific pre-processing steps. Rather than being limited to a single software package, fMRIprep will leverage the best software tool for each pre-processing step, such as ANTS for normalization, FreeSurfer for surface reconstruction, and so on. It's simple to use, and because it's standardized, it provides better transparency and reproducibility. To use fMRIprep, you will need to install the following programs. If you haven't already installed FreeSurfer from a previous tutorial, go to this webpage that I'm opening up right now. As you'll see later, you don't actually need to download the entire software package. You just need the license.txt file, which you can get by filling out this form. This includes personal details like my name, address, email address, telephone number, but I don't want the NSA to see it, so I'm blurring it out. Once you fill out the form and submit it, they'll send you an email, and then you download this license.txt file. The next package to install is Docker. Docker allows you to access containers, which are suites of programs needed to do a certain task. In our case, we can use Docker to include all of the software packages needed for our analysis without having to download each of them separately. Go to this webpage to download the version of Docker for your system, in my case, for Macintosh. This will take a little while, so at this point I'm going to fade out once it starts to download and come back when it has finished. When it has finished downloading, click on it to open the Docker disk image, and then follow the instructions to place it into your applications folder. I've already installed this, so I'm not going to go through that again. But once it is installed, you'll see this icon that looks like a whale with some bubbles on top of it. If you click on that, go to Preferences, and then click on Resources. You can choose how much memory to let Docker use. It is recommended that you give it at least 8 GB of memory and at least a couple of CPUs. The rest of the defaults should be fine. To activate the fMRIprep containers, we need to use pip to install the necessary packages. This is the line of code you'll need to type. I've already done this, so again, I'm not going to reinstall it again, but this will allow you to use the fMRIprep command. Now that we have all of the prerequisites installed, we need a data set. For this course, we will be analyzing an fMRI dataset that used the flanker task, the same one that we used for the AFNI tutorial, so that we can compare the results. The dataset can be found here on the OpenNeuro website, an online repository for neuroimaging data. The OpenNeuro page for the flanker dataset includes a dataset file tree, which includes the folders ANAT, which contains the anatomical image, and FUNC, which contains the functional images and onset times for each run in a TSV file. Note that the data needs to be in this BIDS format in order to be analyzed by fMRIprep. If you have your own data and would like to analyze it using fMRIprep, see the link in the description box down below for a BIDS tutorial. Now download the dataset by clicking on the download button at the top of the page. The dataset is about 2 GB and comes in a zipped folder. If the download button doesn't work, try using the Amazon Web Services or AWS option. Go to this page and download the appropriate AWS client for your operating system. Once it has installed, open a terminal, navigate to the desktop, and type the following. or simply copy and paste it from the OpenNeuro page. It should take about 10 to 15 minutes to download, so I'm going to fade out here and come back. Once you've downloaded the dataset, change the name from this to Flanker. Now that we have the data, we are ready to create our fMRIprep analysis script, which we will cover in the next video. Now that we have all of the prerequisites, we just need to create a script to do the fMRIprep analysis for us. To begin, go to this GitHub page, and the link is down below in the description box. Click on fMRIprep single subject, then click on the Raw button. Right-click anywhere on the page, click Save As, and save this file into your Downloads directory. Now open up a terminal and type makedir code, and then move Downloads fMRIprep to the code directory. Let's take a look at what the code does by typing cat fMRIprep single subject. You should see something like this. The first block of code, under user inputs, first sets the path to where the data is, in this case home desktop flanker, as well as which subject to analyze, which in this case is subject 08. nthreads specifies the number of processors to use, and mem specifies the amount of memory to use in gigabytes. The variable container can be set to either Docker or Singularity. The latter, which refers to a container typically used on supercomputing clusters, will be covered in a later tutorial. For now, we will set it to Docker. The second block of code reformats the mem variable to remove the suffix GB so that it can be read by fMRIprep without throwing any errors. The line of code below that, export fs license, points to where the license.txt file that we downloaded previously is located, so that we can run FreeSurfer in the container. Now we come to the last half of the code, an if-else statement that executes code depending on whether you chose Docker or Singularity. Since we chose Docker, the second part of the statement will be run. Within that section, we will supply both the root directory containing the data, in other words, the flanker directory, and the data where the output will be stored, which we will place in the derivatives subfolder. The other lines of code in this block mostly contain options for your analysis, which we will explore later. For now, we will run a relatively simple analysis which does the standard pre-processing steps of co-registration, normalization, and physiological component extraction. The last two lines, mem_mb and -w, use variables to specify the amount of memory to be used, and the working directory where intermediate results will be stored, in this case, in the home directory. To run the script, make sure you are in the code directory, make sure Docker is running, and then type bash fMRIprep, single subject. This will begin pre-processing the data for subject 8, which, you may recall, was one of the first subjects we analyzed in the fMRI tutorials on SPM, AFNI, and FSL. Our goal here will be to compare the output from those pre-processing pipelines with what is generated by fMRIprep, in order to see the relative advantages and disadvantages of each one. Using the bare bones analysis pipeline that we specified above, this should take about 1 to 2 hours to process. Right now, we're going to fade out, and when we come back, we will examine the output. When fMRIprep has finished, the output will be located in the directory derivatives fMRIprep. Within that directory, we see the folder sub08. This contains all of the pre-processed functional and anatomical data, including intermediate files that were created in order to generate the final product, as well as JSON files that contain header information for each of their corresponding images. Within the anatomical directory, for example, we find these images that have MNI152NL in their name. This means that they have been normalized to that template. whereas we have other files without that string, which means they're still in raw or native space. Moving on to the func directory, we have the following files. You will see two distinct blocks of files, one for each run. The first block contains a list of confound regressors, such as time courses from the white matter and cerebrospinal fluid, located in this TSV file here for run 1. The file sub08 task flanker run 1 space MNI152 and LIN 2009C ASIM res2 is the reference image used for registration and normalization, while the sub08 task flanker run 1 space MNI152 and so on is the estimated brain mask for that run. And the file sub08 task flanker run 1 space MNI152 and so on is the preprocessed functional data up through normalization. Similar files are generated for the other runs in your dataset. All of these output files will be used in the HTML summary, which we now turn to. These HTML files contain a summary of all the preprocessing output. You can open them by using Finder and double-clicking on the file, or using the terminal to type open sub08 HTML. You should see something like this. The layout of the web page is organized into the following sections: summary, anatomical, functional, about, methods, and errors, with corresponding links at the top of the page. First section, summary, contains details about the number of structural and functional images, the template that was used for normalization, and whether FreeSurfer was run. These should match the options you specified in the fMRIprep script that we ran in the previous chapter. The next section contains anatomical QA checks, with the first figure showing the anatomical image in sagittal, axial, and coronal views. The estimated brain mask is outlined in red. The gray matter boundary is outlined in magenta, and the white matter boundary is outlined in blue. These boundaries will be used for component extraction, which we will discuss in just a little bit. Normalization of the anatomical image to the template, in this case MNI152 and LIN 2009C ASIM, is shown in a back and forth GIF when you hover your cursor over this figure. Make sure to check the alignment not only between the outlines of the brains, but also the internal structures, such as the ventricles. We now move to the functional QA, which again uses a GIF to show the alignment between the functional and anatomical images. As with the normalization QA check, make sure that the internal structures are well aligned, remembering that lighter voxels in the functional images represent fluid, and vice versa in the anatomical image. The next figure shows an outline of the masks used for anatomical component correction, or ANAT-CompCore, with magenta showing the white matter and CSF voxels used to estimate signal that is representative of those tissues. The voxels outlined in blue show the most variable voxels, which will be used for functional component correction, or func-CompCore. These voxels are then used to generate CompCore curves for the white matter, CSF, combined white matter and CSF, and temporal variation, which show the amount of variance explained by different amounts of components. The first 16 components of the white matter mask, for example, explain half of the variance within those voxels. You will have to make a judgment about the trade-off between removing nuisance variance and spending more degrees of freedom and statistical power on modeling those sources of variance. Time series plots are also generated for global signal, or GS, global signal of the cerebrospinal fluid, GS-CSF, global signal of the white matter, and two measures of motion, dVARS and frame-wise displacement, or FD. Changes in motion tend to be correlated with changes in global signal, and it is up to you whether to include any of those regressors in your model. In general, dVARS and FD are good ways to account for signal caused by motion artifacts. The next figure is a carpet plot, showing the time series of each major tissue type. Voxels are grouped into cortical, here dark and light blue, subcortical in orange, gray matter and cerebellum in green, and white matter and CSF in red. Any sudden changes in motion may be reflected in uniform changes across the entire column for that time point. Lastly, a matrix shows correlations between different nuisance regressors. High correlations between some of them, for example, let's say CSF and one of the anatomical components, may be explained by motion causing signal changes in the CSF that encases the skull. The bar chart on the right shows the correlation of different regressors with respect to global signal. Those components that show a high degree of correlation may be candidates for nuisance regression. Now that we have run quality checks on our data and have some idea of what regressors to include, we are prepared to begin creating our general linear model. Before we can do that, however, we have the option of running a couple more pre-processing steps. We will see what those are and how to do them in the next video.